Yeah, I got lucky the past few years. For the houses I completely agree with you. I don't need it now. Yeah, seriously. And then we had like a terrifying thing. I'm sure you have to be very like personable.
Okay.
Hi everybody.
So let's talk upcoming assignments. So one is homework this week. How are we doing? Good. Oh, look at that. Either you learn to just like give the response that I expect, which is okay by me, or you really just have learned the true lesson in life that procrastinators never win. No, I'm just kidding. Too much moralizing, sorry. yeah, homework this week. I'll be here after class today, happy to answer questions. And Thursday, TAs have their office hours. Hopefully this one's going a little bit slightly better than, or like a little bit like smoother, you know, like you greased the skids already and now you're, you know, kind of know how to go here. Plus PyTorch maybe is making it easier, hopefully. So yeah, there's that. And then of course, I guess it's next week where we've got project, is it next week? Yeah, project proposals are due. So some of you have been asking me questions about that, that's great. Just remember that no one-person teams. I've already had a couple of requests. I've had to remind people that. We've already talked about this. No one-person teams. Make sure that you are at least in a group of 2, no more than 3. And this doesn't have to be a research project. Hopefully you've been getting interested in deep learning if this is your first introduction to it. And you've got some like ideas that, you know, from just the things that you've seen that you want to try out. It's just really about doing something that's not already in the class, just something that you're interested in, some data set that you've got access to or you found access to, and doing something, you know, different than what's been done. No reproductions of just, you know, existing work, but you can be very close to existing work as long as you're doing something a little bit different, and you know, like you explain kind of what it is you want to do and why it's, you know, why it's different and why it's interesting to you. So follow the rules, you know, the outlines for the guidelines, excuse me, for those submissions, and get those in. It's not meant to be, you know, like super onerous. Just, you know, make a plan, write it up, and I will be reviewing those each one. And what I'll be doing is I will indicate that I have, you know, read it and accepted it by giving you 1 extra point. You get it's a 0 point assignment, but once I approve it, you get 1 extra point. So like, boom, extra points. It's like, I am a good guy. That's what you got to remember. But usually what happens is that there's a little bit of back and forth. You know, like I'll read through it and I'll be like, hey, this looks like really hard. Have you thought about that? And then, you know, I save you from like doing something way too hard. Or sometimes I say, wow, this is way too easy. Or I just, you know, just say like, you know, have you thought about this or that? We just have a little bit of back and forth and then I approve it. So anyways, it's a lot of fun. Hopefully it seems fun. It is a lot of work, but it's fun work. At least I think it is. It's fun to read them in the end. I think usually these are really great, you know, great projects. It's exciting to see what you all think of. So that's due next week. Again, if you have questions about that, happy to answer them right now or you know, after class. So, and then you can always send me emails. I'm a little bit slower on emails because I don't know, too many emails in general. I still get junk mail. Do you? I mean, you guys probably don't get junk. Do you get junk mail? Like, what in the world? Does anybody ever respond to anything they get in the mail? Like an ad in the mail? I don't know. Anyways, a lot of trees being killed just to be thrown away. I don't get it. But anyways, there's a lot of junk email too. So sometimes I get to it and it takes me a little bit of time. I apologize, but I always get to it. Okay. Any questions before we get started?
Can you remind me if we end up presenting our projects?
Oh, right. Good question. We don't present them. As much as I would like to do that, it just doesn't kind of like work. It's like just too busy at the time. Yeah. I have a real job, and like it becomes a really busy time for that. Not that this isn't real, sorry. But I have another job. Yeah, that sounded really bad. Go back, rewind. I have another job that becomes really busy that time of year, and it just doesn't make sense. Plus, hopefully, it's just easier for you to just write it up. Now, the write-up does need to be like well done, since you know we can't go back and forth on the write-up like we could at like a poster board or something like that. So make sure that like things are clear there. But in general, it's fine. People do really well on this because I don't know, they mostly they're invested in the idea, and they enjoy kind of executing on it. So good question though. No presentation, and this is a real class. Yeah. whole dugout. Yeah.
Can be in any format, right? No specific format or something.
I mean, yeah, no, there's no specific format. I mean, there's like suggestions like, you know, like what should be, you know, like when you look at it, there's some suggestions about like what should end up there, but basically this needs to be like a PDF of like just writing up your results and all of the like the code, you know, that you use to run things. This is usually just another notebook that people submit. Sometimes people go all out and there's like all kinds of scripts and stuff, you know, submitted and, you know, and zipped up. Whatever. I just need to see that. I just need to see the code and everything that you used to do it. I don't try to rerun it. That's just too many things to rerun, but especially this year. We have a lot of students. We have nearly 100. Some people backed out at the last minute, so we don't have 100. We have like 97 or 98. But last year we only had like just under 60. So I have a lot more reading to do this year. Anyways, I won't be rerunning them. I'll believe that you actually ran them just by seeing all the code and things that you submit. So you could totally fake me out. I'm like a discriminator. Oh, we haven't done GANs yet. Well, when we get to GANs, remind me, and I will tell you about I'll be the discriminator. You can be the generator. We can have a little adversarial fight and see how that goes. But usually, like, yeah, just the write-up is. I spend a lot of time just kind of going through your write-up and, you know, making sure that you've kind of executed on what you plan to do. Cool. All right. Should we get started? Any more questions? All right. So, as promised, transformers. Should have got that a little bit sooner, because like somebody might think like this was like a course on like, I don't know, toys of my childhood or something like that. I am old enough that I like played with Transformers when they first came out. Yeah. So I am getting older. It's a weird thing to say, but yeah, like when there were GoBots first, and then like just like everything, like the first iteration's like cool, and then somebody's like, I can do that better, and then they like dominate. And now there's movies and everything. But anyways, GoBots, yeah. Then there was Transformers, Optimus Prime, always a personal hero. All right, but for some reason we don't get to see the cool Transformers. We just get to see these Transformers. So last time we talked about advanced neural machine translation. So, you know, blah, blah, blah. The important part is sentence length problem, the attention mechanism. Remember, yes, attention. Remember what that was? This whole thing about attention was allowing the cell that needs to produce a new hidden state access not to just the previous hidden state, but to all the hidden states, like in the encoder in this seek-to-seek architecture, sequence to sequence. And this allowing access to it was something more than just like, I don't know, just going and grabbing them and putting them all together, but there was a learned component where we said, well, what if we just allowed the network, the architecture, to learn a linear combination that was conditioned on this previous hidden state in some learnable way, that when incorporated into here, you know, was expected to give a better result than if you didn't do that. And so that's what we did. We introduced attention. That's what was done. We described this. We saw how this allowed for much better performance, in this case on translation tasks, on longer sequences. This allowed for this ability to kind of have access to the different states of the encoder, hidden states of the encoder, allowed us to do better in terms of like translating between languages as the sentences got longer and longer and longer. And you know, the intuition there is just simply that you know, the previous hidden state just isn't enough to be able to encode all that information, you know, in terms of like an updatable state, that we needed access to previous information to make that even better. And you know, this is proof that that is the case. So cool. So that's attention. here's a little, here's what we looked at before, just in a different format. We have our hidden states from the encoder. We have our decoder hidden state at whatever time step. This says time step 4 because I grabbed it from some existing slides that say that was doing this at time step 4. But whatever, it's at time step n. And the idea was that there was some way of comparing. This is usually looks like a dot product, but you could have something fancier there if you wanted some sort of MLP that combined the two or whatever. MLP is multi-layer perceptron. Exactly, thank you. So just like a small feed-forward network, but whatever, some way of combining these two that produces a score. Usually this is dot product, so the more aligned we are, the decoder hidden state with the encoder hidden state, like the more we want to maybe use that or something, whatever. But some way of producing scores, and normalizing those scores so that we get, applying softmax so that we get a distribution, meaning non-negative coefficients that sum to 1, and then we create a linear combination of these using these learned attention coefficients or attention weights. And so the picture here is like, this one's large, this coefficient's large, these two are small. So when I multiply this hidden state by this, I basically have the same, get the same thing again. But when I multiply this by this is a very small contribution similarly here. And that I sum all these up into a context vector, that convex combination, and then that is then used as my input, or can be additionally combined with this again as my input or as my hidden state for that stage of the decoder. And so that was done back in 2015. People started using attention in a lot of different places, a lot of different architectures. Just this idea of like being able to have access to these previous states in an encoder. So we haven't actually really done autoencoders yet. That's coming up in this class. But this very often there's this idea of like encoding something and then decoding it. So encoding something to some kind of representation or code or embedding, as they're often called, and then decoding that back to the original state. And so wherever that kind of an architecture existed, people were starting to use attention, and it was helpful. And then all of a sudden in 2017 this paper came out, and it was called "Attention is All You Need." This really sparked like a whole series of papers. There's all kinds of papers that are like "Wildcard is all you need." But "Attention is all you need" was the first one, and they propose the transformer architecture, which this is from that 2017 paper, and this is like whenever you see transformers reference, you see basically a picture that looks like this. And today what we're going to do is we're going to go through this computation graph basically, and understand like what on earth's going on here. But if attention was helpful, in that translation task, basically what this architecture did was just basically have attention as the only mechanism throughout the entire architecture. Wherever, what you'll see here is like many layers. So this nx is saying like there's n layers of whatever these cells are here, and notice how each one of these has a multi-head attention. So there's going to be lots of attention on each one of these cells, and then we're going to do this multiple times. This is the encoder, and when we decode, this is on this side. We're going to have this is showing a balanced number of encoding layers and decoding layers, but it doesn't have to be that way, but it's typically done that way. That we're going to have again lots of attention mechanisms, and that's going to be it. There is this feed forward part in each one of these cells that we'll also talk about what it's doing, but it's basically attention is everywhere. So it's called "Attention is All You Need" because these architectures are made of basically only attention. Now it's a little bit different from what we saw before. This is known as self-attention, and we'll talk about what that means. It's kind of weird actually when you first see it, because it's like, how can that be helpful? But this sort of sparked, really what's been the kind of the next architectural revolution in deep learning. Architectures like this are what back all of the really cool language models that you're seeing today, whether that is something like, GPT-3, which came out already now, a couple of years ago, what was it last year? Oh, no, I can't remember. Anyways, not too long ago, or a little while ago in terms of, deep learning history, but that like are amazing, models from a number of different perspectives. And we're going to talk more about them, like what they're doing. We'll go through a little bit of like next time the history of these kind of like building up the GPT architectures. But importantly, what these are able to do is that you're able to create a lot of capacity in a single model, like having like a single mechanism kind of repeated over and over again. In a very general yet powerful mechanism allows for these to be huge models that can then be trained effectively on huge amounts of data to then be like fine-tuned to do all kinds of tasks. Like you think about language in general, like these are trained to do, we're going to talk about what this training is, but like these very general kinds of like self-supervised tasks. But then they get fine-tuned and they can do all kinds of really crazy things. And what's really cool about things like GPT-3 is that they seem to have like emergent behavior that wasn't anticipated, but just kind of emerges from having been trained in on so much data in such a general way, where you get really interesting things like few-shot behavior. So like you give a couple of examples of a pattern, and all of a sudden this transformer architecture can produce language, can generate language that follows that pattern. And it's as if it's learning how to do a task. It looks like it's learning to do a task by just being given a few examples. And of course, this is like the holy grail in some sense of what we want to be doing with AI in general, is that like humans seem to be able to learn to do tasks fairly quickly from only a couple of examples. I mean, maybe not in an expert fashion, but like if you think about just kids, they can learn to play all kinds of games, really quickly. They only need a couple of examples. They can learn to like use language, in fairly effective ways, even if it isn't perfect, with only a few examples. And there's lots of cool debate about like how that really happens. But the fact that transformers being trained on so much data can kind of like exhibit even a little bit of that kind of pattern of behavior is really exciting. Now, this isn't artificial intelligence. This is just another really powerful network that can like learn statistical distributions that are in the data in really kind of powerful, intricate ways, but fascinating nonetheless that it can do this. So all that comes from just a bunch of arrows and boxes, as shown right here. So what are these arrows and boxes? Well, we'll be getting into that during today's class. Note that when this came out, we have blue scores for the English to German and English to French translation tasks. Like we've seen the blue scores for this, looking at the RNN seek-to-seek models, and notice that the blue scores, especially for the big transformer, which just means many more of these layers, are state of the art. Like they are the highest. Now they're actually not like that much larger, say, than what came before. Like especially if you think about this French task, like this isn't that much more. But of course we don't really have a good concept of what like one unit of blue score really represents. But this was just like kind of out of the gate doing this, and then since this time there have been all kinds of different forms of just different varieties of transformers that have really been able to push, these numbers far like higher. And so, and this especially just comes with just making these networks larger and pre-training on a lot more data. Anyways, so that's kind of the context for this. 2017 was already 5 years ago, so ancient history in deep learning terms, but really the basics that we're going to look at today are at the core of so many of the state-of-the-art models that we see today, mostly in language, but also more and more in vision as well. Okay, so what is this architecture all about? What's going on here? Well, let's just kind of walk through this really quick. So we're going to have inputs just like we've had before. We're think the canonical example here to just think about is think about sentences. Each word in the sentence being a token, and each of those is going to become an input to the model. Okay, so this is very similar to RNNs, but different from RNNs. RNNs, remember, RNNs sort of have this what we call autoregressive like inductive bias to them, where you need to put in the first token, then you put in the second token, and then the third, and so the model is learning, to aggregate the state of that thing that it's, the state of the sentence as it's being given each token one by one in order. Here you input everything all at once into the model, and in some sense, what that means is that the model from the beginning, from the input, has access to all the tokens all at once. Now, in certain structures like time series and sentences, the order still matters. And so if you didn't do anything about that, you'd basically be learning something that was taking in a set of things, and then the output would also be just to a set of things. But because these things were proposed in the context of language where you do have this ordering, you'll see different aspects. We're going to see that we'll talk about as we go through, but you'll see different aspects of that kind of deal with that. So the first thing here are these positional encodings, and we'll get to this later in the lecture. But there's a way. It's very strange when we see it. Hopefully you'll go, what is that? That is so weird. But if you don't, and if you just intuitively get it, come tell me, because you're probably a genius, and I just want to shake your hand. You put this thing, you add to this some kind of additional encoding to the encoding of each of your tokens that gives it some positional information. It's some way of indicating that hey, I'm the first token, I'm the second token, I'm the third, and so forth.
When you say give all of the input at once, there's intrinsic ordering a vector
Yep.
to begin with. So
To a vector?
yeah, because
Well, each of the vectors itself is a token, the whole vector.
Oh, okay.
Yeah.
So you just pass in everything.
You're gonna pass. So if my sentence is n, 10 words long, each of the embeddings for each of those words is input into the model all at the same time, essentially.
Yeah.
But we indicate ordering through this additional position. It's called a position encoding or positional encoding, and it's just kind of this weird thing that literally is added to it. It is weird. I still don't have a great understanding of why that and not something else, but it's what was done, and it's more or less used still today to indicate this kind of ordering. So that gives some information right up front about the ordering, and that's kind of preserved as we decode as well. You see this information here. But then we do this multi-head attention. There's a call out here to the multi-head attention. So what is multi-head attention? Well, we're going to spend most of today talking about that, but basically it is we take this input, this set of embeddings for all the tokens, and we are going to create three representations of that. One known as the values, one known as the key, and one known as the query. And these are used like these words are used in like an analogy to, like, if you know something about like document retrieval or any kind of query format, you have these notions of like, I submit a query, you know, to like, I don't know, my database or to my you know, set of documents or whatever. There are keys that represent those documents or those entries in the database or something like that. And my query, we do some kind of comparison to those keys to be able to find the thing that we're looking for. And then these values are the sort of like the output we want if we find that a query is close to a key. So this is sounding a little bit like what we did already, thinking about the original attention mechanism, where the query was our current decoding hidden state, the decoder hidden state. The keys were the hidden states from each stage of the encoder, and this values is a slightly different thing, where the keys themselves were used as the values in the original attention mechanism. Here we allow for there to be something different from that. But how we get this is like the simplest way, the way that we do everything in neural networks, which is what we're just going to do. We're going to take our input and we're going to do something to it to give us values, keys, and queries. What do you think it's going to be?
Product with
Oh, that's awesome. Really, yeah, that's basically it. We're going to multiply by a matrix, by a learned weight matrix. We're going to take this input. We're going to multiply it by a learned values matrix, a learned key matrix, a learned query matrix for this particular layer. And this will produce, you know, the corresponding values, keys, and queries. We'll then put this all together to compute the attention coefficients, and then you know, like the resulting like output of that, like the hit. You know, you can think of it as like the hidden state coming out of this attention. This thing about multi-head is that we're going to do this multiple times. So there's going to be many of these matrices for producing these keys, the values, keys, and queries. Think of that as kind of like the different filters in a convolutional layer. And then the output of all of those, we're going to sort of, the hidden state of all those, we're going to put those all together, concatenate them all together, have one more linear projection, so like multiply by another weight matrix, to then give us like the total output. And we're going to go through this step by step. I'm just telling you about that now. And that's what it's going to be. So like literally it's like take input, project it 3 different ways, h different times, then concatenate all that. Yeah, so project it, compute attention coefficients, get a hidden state for each one of these, concatenate those all together to give you one hidden state for the multi-head attention, project that to give you the final hidden state that then comes out of this arrow right here. And then we have this interesting feed-forward layer that it's really interesting. It actually expands the dimension, and then we contract it again. It's kind of an interesting thing. It actually was necessary in the original formulation. Kind of debatable, like whether it's still necessary, but you see it very often in the architectures. And then that is that's the output to the next, either the next encoder layer, or then, you know, once we've gotten through all the encoding layers, we then input that. Those become inputs to the decoding layers. Now, notice some other things that are happening here. So this is like that V, you know, Q or K and Q. Why there's those 3 arrows. But notice that there is this other arrow right here that's going from basically like from the input around the multi-head attention. Guess what that is? Someone's. Yeah, it's a skip connection. It's a skip connection. So these are going to be deep networks. So this has skip connections here and here. To do guess what? Exactly what the skip connections did in ResNets, and what they do like in the LSTMs along the C track, and that is just to allow there to propagate gradients through all these layers effectively. So notice, so this is kind of interesting, right? Like there's a bit of history of how the architectures that have stuck in deep learning through the last 10 years have like come about, like some key ideas, and this idea of skip connections, these you know, like having these like residual connections that are sometimes called, is key for deep networks. And so ResNets, you know, were the first to kind of really make those popular, you know, show the value of them, and you see them now in all kinds of architectures. So you have that here, both here and here. Notice there's also a norm here. Guess what that is? Yeah, it's not a batch norm. It is a normalization layer, but it isn't batch norm. It's a layer norm, but very similar to a batch norm. The idea is the same. You know, the idea is that we're normalizing the output there, so that the distribution of the input after that normalization into the next part of this network, and then, you know, here as well, is a little bit more the expected one, which relieves the burden of learning on the next layer. So like, again, you know, batch norm was introduced, you know, earlier, as we saw when we were thinking about, when we were going through the history of you know, computer vision, and those similar ideas exist here. We also have nonlinear activations, but they tend to be, oh, thank you, man. They tend to be in these architectures, they tend to be of a different type, GLUs rather than ReLUs. So this is a Gaussian exponential linear unit, but the idea is pretty much the same. You have this simple nonlinearity that is mostly, you know, it's mostly linear, but, you know, it has, wherever it's nonlinear, it's fairly simple and really aids in the training of this. So like, all these different ideas are coming from previous, you know, successful models, and are incorporated here, again, to make, you know, to make the training of this network, you know, efficient, you know, effective. And so, you know, many times, like in this course, students rightfully ask, well, like, how do I choose, like, if I'm going to make a new architecture, like, well, how would I know to do this kind of thing, you know? Well, I don't know that you know how to do, you know, you think of this, but remember, like, all this really is combining ideas, like a bunch of ideas that just seem to work other places. So, you know, the hypothesis is attention is a really powerful mechanism. Like, what if we just kind of had attention everywhere? What would that be like? And then, you know, we want to have these deep networks. We know we need to have like simple nonlinear activations, kind of like ReLUs. We need to have skip connections. We need to have normalization and so forth. Right. So, so while it looks like, you know, you could maybe choose whatever you want, and like maybe it would work. Really, the same kinds of ideas kind of appear over and over. Okay, so that's encoding. You go through. So each one of the like encoding modules has these two layers in it, and you do this n times. Like this number right here is typically like, for like standard transforms, this might be 6. As they start to get deeper, that might be 12, 24, something like that. Encoding layers, and then you typically have as many decoding layers. And so what happens here, we want to be, like a typical task here will be to like predict the next token in the sequence. And so we need to input our output, the input to the decoder is our output embeddings, like similar to this. We'll have some positional encoding of them, but of course these are going to be shifted, right? So like, if what we want to do is we want to predict, so one thing to say about this, I don't know if it's clear from here, is that the output of this, well, we'll see it in the next slide. The output of this, if we have like n tokens here, we have 10 tokens here, the output of this is going to be it's going to be 10 tokens, 10 vectors associated with those tokens. And so we kind of preserve that. Now, obviously, like all the information from all the tokens is getting kind of mixed up in these layers. And so, you know, the thing that comes out here is not necessarily just like, just some information about that particular token. It's all mixed together. But depending on the task, like what that information will be, or sorry, I should say differently, like what information that is encoded there will depend on the task. So if the task is to do something like what we've done before, is where we want to predict the next word, you know, the input to that will be our, you know, the input to the encoder just shifted so that the thing that the first thing here is like the second thing here, right? So that those tokens are lining up, and then we just do kind of the same thing. We just have some slightly different. We have some slightly different pieces. We have what's called masked multi-head attention. So this masking has to do with the fact that when we're decoding, like if we want this to be like a generator, we can't generate a word. Like we want this to work as a generator. We can't generate a word that depending on a word that came before or came after, right? We can only generate things and then have those things depend as we're decoding on words that we already produced. So if you think about like when we were doing the English or the English to French, that you know we would produce the first word and that would become like you know input for the second word. So we have this masked multi-head attention that like basically imposes that some structure. We'll talk a little bit more about that. And then we have another multi-head attention here, but it turns out that the keys, that the values in keys now come from the output of our encoder, and the queries come from here. So this is a way of making the decoding depend on the encoding. So that's why the arrows are coming out of here for two of the arrows, and then one of the arrows is coming out of here. But then everything else is the same, and you do that over and over and over again. So like we continue to condition this particular multi-head attention in the decoder on the encoding tokens. Okay, so we're going to go through this more carefully, but then note that just at the very end, guess we do a projection to a linear projection to, you know, for each of the tokens to, in this case, if we're doing the like predict the next word, to a softmax over our vocabulary, and then we now have a classification problem to predict the correct word that should show up there, you know, depending on all that, all of the state that we've accumulated through the encoder and decoder. So it looks a lot like the sequence to sequence. It's just that our encoder and our decoder are now way more complicated in terms of like their mechanism, and it ends up just being a bunch of this kind of self-attention over and over and over again.
Sorry, zoom out question.
Yeah.
Are the outputs that are coming into the decoder outputs from the encoder on the left?
Mm-hmm.
So the encoder
Like
is
these arrows right here. Is that what you're asking about?
those arrows, but then also the output.
This right here?
Yeah, those. Where do those?
No. So like this is basically for the problem of wanting to predict the next word. This is just the inputs again, but shifted. Yeah. Okay. Good question. Okay, we're gonna go through in more detail now. We've already been through like half the lecture, or maybe even more. So we gotta catch up here. But any more general questions or high level questions? Yeah.
So if the input to the decoder is just the inputs but shifted to the right, do you run this n-1 times pretty much? Like, is the output of everything the probabilities for just the one token that you're predicting, or is it predicting the whole sentence?
Yes, this is really interesting. It's doing the whole sentence, right? Because again, you're inputting the whole thing here. But if you want this to behave in the sense that you don't want the predictions for like this first word to depend on any of the other words in the sentence that come after it, then you do this masking here that basically like the masking here sets to 0 all the attention weights that are coming into this token from the other tokens that come after it. So there's a kind of like, it's actually like kind of an upper triangular, well, it's like a lower triangular mask that makes it so that we no attention from the words coming after any word so like no influence through the attention coefficients can influence can be like integrated with the token associated with that word. It just makes it so that whatever information we're integrating through this only depends on things that have come before in the sentence and not after. So that preserves that like natural dependence in the sentence, like left to right in English, that needs to be there if you're going to generate language. So I mean, we'll go into more details here, but that's why this is called masked right here. The masking is to add in that like what we would call an autoregressive inductive bias into the decoding that says we can't decode this particular token with any information from tokens that come after it. Yeah. So I don't expect that to be like, oh yeah, like that. Now I get it. Just yet, because like that's kind of a weird, idea. But that's the point of like today and next, in lecture next time to go through those details.
So just in terms of dimensions, I get that the multi-head attention has like that layered, similar to convolutions coming in. Does the concat or the linear reduce that to like a two-dimensional?
Yeah. So again, we'll see kind of a diagram of this, but like when you concatenate this is going to be some huge. It ends up being a matrix. The point of the linear layer is to project it down into the right dimensions, so that coming out of here, the dimensions are correct. So like basically, like the dimensions in and out need to be the same throughout this whole thing, and that's the job of this final linear layer, is to do that final projection to the right, vector space, the right dimensions, so that that characteristic is preserved. Good question. Okay, let's go. Get into this more. Oh, I didn't really say anything about more of the. Oh, like twice on one slide. This is a new record. We'll talk about this. All right. So, what are we trying to do here? Again, the idea is we have input. Like it's good to think about this in terms of like the problems we've been looking at before, this translation problem. We want to input, say like the tokens from a particular language, and output the translated tokens in a different language. Okay, that's our job. Same as before. Think about the recurrent neural networks, and that we have that recurrent encoder, that recurrent decoder. But here, what's different is that you really no longer have recurrence. At every layer in this encoder, you're allowed to mix all the information together as you encode from layer to layer. And you sort of have the same thing on this decoder, but we enforce the autoregressive nature of language by masking out some of the attentions, meaning that, again, no information from tokens that follow a word can be used in decoding that. Okay, so like that's the idea. That's the setup. As we already saw, this is now just kind of a little more compacted. Our encoders look like this. We have what we call a self-attention layer. Oh, there's a lot going on in this one layer. Lots of operations, and then we have this like expand, contract, feed forward layer. In the decoder, it's almost the same, except that in our multi-head, or in this attention layer right here, this is the tokens from the encoder are input here, so that the decoder is conditioned on what the encoder has produced, right? Like we need to have that. So in the RNNs, that was just the passing of like the hidden state at the end of the encoder to be the first hidden state in the decoder. And then, of course, through attention, we had additional conditioning on all of the hidden states before that. So, this is like an extreme version of that that's allowing for, at all stages in decoding, access to the tokens of the encoder, or the embeddings of the encoding. So, what does this look like, kind of at a high level? We're going to input whatever these things are. These are a little more complicated. Like they're the something like a word embedding, like we talked about before, but they have this positional information. We'll get to that a little bit later. but they go through self-attention, they produce, vectors, representations of these of a fixed size. We go through the feed forward, there again, of the appropriate size to match this, and then we just kind of, do that over and over and over again in the encoder, and then eventually pass that to the decoder. Right. So input embedding, like intermediate embedding within the layer, and then the output embedding from this particular layer. That becomes the input to the next layer. Okay, so what does this look like? All right, so I mentioned this before, and it's multi-head attention. So we're going to be thinking about like what one of the heads of the self-attention layer, what does it look like? So we have our input, whatever these embeddings are that represent both the content of that word and then its position. And then we're going to produce these intermediate representations of them three different ways, and we're going to give them names: query, keys, and values. And this, again, the simple way that we do this is that there's a weight matrix associated with queries, with keys, and with values. These are all different, and they correspond to just this one head. Okay. And literally, that's what it is, right? It's this linear projection of that token to the query space, the key space, and the value space. So again, it's just it's these matrices multiplied by these representations to give us these other representations. So simple so far, but the question you should be asking is like, why queries, keys, and values? Why do I want all that? Oh yeah. So we'll answer that next. This is just to remind you that for each of the heads, we're going to have a different set of these projection matrices for queries, keys, and values, right? So like these, think of these as like filters in a convolutional layer, right? We have multiple filters, for learning different, different features of the input. Sort of the same idea here, although these aren't convolutions. These are matrices of full size to take us from the input dimension to the output dimension. So these are, this triple is different from this triple. So like each of these heads can learn to like create, queries, keys, and values in a different way from another head in that same layer. Okay? So think of that as like an analogy to the filters in a convolutional layer. Make sense? I mean, hope we have enough familiarity at this point to kind of see the similarity there. And then what happens? Well, we do this operation. So we take our input, our sequence of inputs here. We have 2 tokens, but it could be a lot more. And we project that 3 different ways. In this one head, we're going to use the same query matrix to give us the corresponding representation, the corresponding queries for the 2 inputs, the corresponding keys, and the corresponding values. And then what do? Well, this is starting to look like attention. So we take the queries and the keys, and we're gonna produce a score, something that's going to compute. Oftentimes, the way to think about this is the similarity, and then like in transformers, it's always just a simple dot product, right? That's a very simple way of thinking about similarity. So we compute the similarity between the projected query and the projected key, and we get a value. Okay. There's a normalization value that is the square root of the dimension here for these, just shown as the dimension of keys, but these are often all the same dimension. So there's this normalization factor that just is helpful in producing like the right kind of sensitivity to the values that are produced here. And then we apply softmax. So that's all kind of shown here in this part here. So this looks very much like what we were doing before with attention. We produce a score. The score is both the dot product and the sort of normalization, and then we apply softmax. So what we're getting is a distribution over those tokens, right? So in this case, the way that this occurred, actually this is kind of funny because these two numbers here don't really correspond to these two numbers. But anyways, gives you distribution, and then we're going to create a linear combination, not of the keys as we did before in the attention that we saw for seek to seek, but we're going to use these to create a linear combination of the values. So now we use these projections of the input. Okay, so these two projections give us like these attention coefficients, these attention weights, and then they're applied to these projections, the values, and then that gives us the context vector, the analogy of the context vector in the attention mechanism that we saw before. Yeah.
I guess I'm confused why we're using like 3 of them, like Q, K, and B. Like, why couldn't we use a bigger number after more information?
Like
why? What if we had like another?
Like if we just had we had another projection here and somehow used it in here. I mean that's a good question. Not a bad research, like question or like a final project question. I don't really know the answer to that, but the reason it was done this way is because they in doing it this way they follow the analogy of the original attention mechanism, right? Where you have some way of computing your attention weights, like how much attention you're going to pay to these things, and then creating a context vector from that. So this is actually more general than what we saw before, because it's allowing. So instead of this just having 2 projections, and then we create the context vector from the keys, we create these from like an additional projection. So this is actually more general than the mechanism from before. So like it's allowing for there to learn something in addition to what was proposed before. But it's a good question, like why this and not something else? And the truth is, like, there's been a lot of papers that have come out that are wildcard is all you need, and have shown that like you can replace all of this attention stuff with very simple mechanisms that just sort of allow you to sort of extract some kind of information from these in this kind of parallel way, multi-headed way, that like in certain contexts can be shown to perform as well as the attention mechanism. So I mean, this gets a little bit beyond like the scope of what I'm trying to like do here today, but there's a whole bunch of, there's like a cottage industry of like wildcard is all you need, and they just kind of follow the same architecture but replace these with, I mean, like very simple things like simple MLPs, so like again like simple like feed-forward networks, like simple pooling operations, and as long as you kind of have enough of these, both in parallel and like layers of these, like these extract the right kinds of information to be very powerful learners. So like in some sense, nothing really special about attention, but on the other hand, like this is the thing kind of everybody's still using because, I don't know, it was first, and it still is like the best, I guess, in like at least some ways of thinking about it, but I don't know. So it's kind of it's kind of a weird thing to say, like, hey, attention is really exciting, then I tell you that like actually you can do a lot of different things here, and attention is not that exciting, but it really is exciting because like this is kind of, despite those papers, everybody's still doing this, and maybe at some point someone's gonna say like, well, it's way better to go something else, and we'll do that. What's nice about this is this looks very much like it's very interpretable in some ways, like what's happening here, right? It's like, and the words here give you, like, help you think of the interpretation, right? It's like, we come in with a query, we compare it to, some keys, the value we want to extract is now going to be, you know, the measure of similarity between these things on, you know, from those values. So you could think of these as all being like keys and values being kind of pre-stored in the database, and this query is a way of like going to get the thing out of the database. The weird thing about this though is that like each one of these things is just a projection of the original input. So it's not like this has been pre-stored, you know, it isn't like this has been stored someplace and we're just going into query with something else. It's like we're literally using the same, all these are dependent on exactly the same thing. So it's kind of got this weird feeling of like, you know, like how can this learn anything really interesting, because it's all conditioned on exactly the same information. But again, because we are able to learn these parameters across many heads, across a whole bunch of layers of these things, it just, in analogy with like filters in a convolutional layer, and many convolutional layers, it just allows for really powerful feature extraction. So I don't know. Long answer to say basically I don't know. Here's me just kind of winging why it's this way, but yeah, it you know, in general this works really well in the sense that it is the key architectural pieces of the best networks that exist right now for certain kinds of problems. You do this for all of your inputs. Like we just kind of showed this for this example right for computing the context vector for the first input, but you do exactly the same thing for the second input. Just replace all the 1s with 2s here. Oh no! Oh, I should have said this. Notice that the key here. The reason why this is being shown over here is that we are comparing the query coming from the first input with the key from the second input here, right? And so this is now how we build in the dependence across all of the tokens. Is through this query coming from one input, key coming from the other input. And I'm just showing it for 2 here for simplicity, but of course you would do this if you had 10 inputs. You'd have these scores across all 10 inputs, giving you, eventually, attention weights across all these 10 inputs. Then you linearly combine all those values using these coefficients. So whether it's 2 or 10 or 100 or 1,000, it's all the same here. And that's how we get the dependence in these attention layers on all of the inputs. Make sense? That's where it comes in right there. Well, and also through the values as well, I guess, because of you're multiplying the transformation of this to that. But that's where that's coming in. That's how you get that dependence. And this is different, again, remember, this is very different from when we are encoding using a recurrent neural network, because when we encode the first token, we can only do that conditioned on just the initial hidden state, which is usually just like zeros. It doesn't have anything to do with the sentence. And then when we're encoding the second token, that can only be conditioned on the previous hidden state, which has information about the first token, and so forth. The nth token only can be conditioned on the previous n-1 through the n-1 tokens through the hidden state. And then via attention through, man, look at me go. Through attention, you have access to, when we get to decoding, to the previous states, but it's autoregressive. You only have access to what's come before. Here you have access to the whole, to all the input. And that's one of the reasons that this is thought to be a more general architecture for this kind of data, is because you are doing this encoding in the context of all the input. Okay, so this is the mathematical way of writing down what all of this is all at once. This is our dot product of all of our queries with all of our keys, all normalized, applying the softmax. Row-wise, is that how it goes? I guess it just depends on it just depends on whether these are containing, yeah, row-wise, exactly, because of the way this is here. So then applying that softmax, that gives you all the attention weights. So once you have the attention weights, you can the output of this then are these like intermediate encodings, and each of those heads is going to give us, for this for this matrix of input, where each row is corresponding to one of the tokens in the sentence, we're going to get a corresponding like hidden representation, same number of rows, but possibly different dimension for those embeddings. And we have that across all of our heads, whether that's 8 or 24 or whatever. And then what do we do with all those? Like I said before, we concatenate all of those into one just large representation of the input at that layer. But the trouble is that we want this to be of the same size as the input. So we need to then, as was mentioned before, we need to then to do that, and the simple way that we do that is just we have one more in this layer, one more learned set of weights that is a matrix that when we multiply it times this, we get the output size of one here. In this case, like we preserve the number of rows, but we have the right number of columns that corresponding to the size of the input embeddings. So, makes sense? No matter how many heads we have in this attention layer, the self-attention layer, we're eventually going to bring it back to the same dimension as the input was originally, simply by just projecting it through another matrix multiplication. So I guess, again, another like principle of building up powerful neural networks is you don't, like, the way that these operations depend on the parameters is often just through simple matrix multiplication, just these linear operations. The nonlinearities that are required to have, for these things to represent nonlinear functions are simply brought in through simple nonlinear activations. Questions? Does it make sense like what this is? This is each one of these is just the output of one of the heads. Concatenate it all together, project it down. There's your output. It's just linear algebra everywhere you look. It's not even just linear algebra, it's just like linear arithmetic. It's just like multiplication. Okay, so if we look at this all together, we have our input. For each of our heads, we have the query, key, and value weight matrices. Doing the multiplications give us the query, keys, and values of each of the heads. Each of those is going to give us an embedding or a hidden representation of the input. Each of those heads, we concatenate them all together. We multiply by one more weight matrix to give us an output, so a hidden representation or an embedding of the input of the same size. And we're just going to do this over and over again. Now we actually have we're going to feed this through just a simple like feed-forward network, just a couple of linear layers. But anyways, this is the output from the self-attention. Make sense?
If you have like a different number of tokens in your input, would you need a different matrix?
No, right? Because if you have a different number of inputs, it's just going to create the more rows. So these, everywhere you look, these will all have more rows. But what we're controlling is the columns, right? That's the dimension of the embedding. Right? Each one of these is an embedding. So it's the number of columns. So whatever this is, whether we have 2 inputs or 100 inputs, this is going to map us to, it's going to preserve the number of rows, but give us the right number of columns. Seem too good to be true? So what does this mean? Like what's happening here? What this is, it's good to not lose sight. So as we're encoding a sentence, we have all these words. So like here's an example of this. So this was our original input. It's some representation. This is taken from the original paper, by the way. It's some tokenization of this sentence that we're trying to, translate or something like that. And so it has some kind of interesting things in it, like keeping track of certain. When you tokenize this, you have some interesting choices to make. So you have this interesting, like we tokenize the apostrophe, but whatever. So what does self-attention mean? Well, whatever layer I'm at, I have a token at that layer that is in the same position as these original input tokens. And what we can say is that for the token, for the token at, like in this case, at this layer, or in the output of this layer right here, how did we get to this, to like the actual values in the representation of this token? Well, it's in some kind of funky way, it's a linear combination of the tokens, the input tokens. And so we can look at those attention weights. They are ordered in this way, and we can say, like, which of these did and at this layer did this token, like, did the representation of this token rely on to create that? And you can look at these for different heads and see what they're doing, and they sometimes this can make sense. So we look at this, like, what does it refer to in this sentence? So if we read this, it says the animal didn't cross the street because it was too tired. So it in this case refers to the animal, not the street. So notice that the weights associated with things having to do with the animal, so like the animal itself, and then things about like what the animal is or isn't doing, are having some kind of positive impact, or like these embeddings are what are being attended to when creating this representation. And other filters or other features might be suppressing some of the other nouns that are in the sentence that this could refer to, but that it doesn't want to. And that's the difference between the orange and the green in this picture. So anyways, like the intuition here about attention is that at each of these layers, this is allowing the creation of the representation at that layer to depend in this self-attention way on all of the tokens. And what we're hoping that it's learning to do is understand, like, the way that language really critically, the sequence of tokens here, contributes to that. And this is like a somewhat interpretable example of that. Although, quite honestly, it's just really cherry picked. This can sometimes be really difficult to understand, especially at deep layers. Okay, so we have a couple minutes left. What are some of the other aspects of this? So the positional encoding. So I said something about if you don't put any information about the ordering here, then if you think about this, this is just like big matrix multiplication. So like in some sense it doesn't really care because each token has access to all the other tokens. It doesn't really care about the ordering. Another way of saying that is like if you rearranged the order of the inputs, then if you don't have some sort of like positional encoding of those, some way of indicating in which position these things are, then just some if you permute the input, then you can permute the rows of all the matrices and get exactly the same, like in a corresponding way, and get get exactly the same representation. So it's in general, this is like a set to set way of like set in, set out. But we do want there to be information about the position because our sentences do have, the order does mean something. So how is that done? Well, you could think of like a lot of ways to do that in the encoder. But the way that this the way that this was done in the original paper and persists today is that you literally add to this a fixed vector that represents the first position, the second position, the third position, and so forth. You add it to whatever is like your word embedding for each of these words. So this is again quite different from the RNNs, where just the word embedding itself was the input representation, but it's that plus something that represents the position. Now, what is that? What is that? Honestly, this is kind of crazy what is done. So I don't I have the formula for this? I don't. Whoops. I should go add that back in. Anyways, there's this formula that basically looks like a discrete Fourier transform of basically like the position of this token, and you're kind of seeing something about this here. So the idea is this: what this vector looks like depends on the length of the sentence and the position of the word within that sentence, and you get something that looks like a discrete Fourier transform. It's basically like you have an e to the I pi kind of, and then some representation of, or some I wish I had the, because I can't remember what it is right now, but you have some way that the position and then the total number of possible tokens comes into this, and it gives you some kind of wild vector that that can look like something like this depending on the length of the sentence. So like if we have a two sentence. If our sentence has two tokens in it, this would be the two positional vectors. If it has three, then this would be the first and the second, and that would be a third, and so forth. And it's honestly why this was picked. I still have never seen like an explanation of it that like sort of justifies exactly why it should be like this. It is a way of making sure that no matter what the length of the sentence is or which position you are in, you're going to get a unique vector that somehow corresponds to something like a phase within some kind of periodic sequence. But honestly, I don't have a good intuition for it. And but you add it to it, so you get in this case for like four-dimensional encoding and 3 tokens in the sentence. These are the vectors that you would add to it, and somehow that works. Now again, you can do like what are known as ablation studies and pull those out and find that it's harder to learn to do as well on the task of say like reconstructing the sentence like translating the sentence in a different language, and you can show that like you could use other types of positional encodings and they may not do as well, or they may do as well. It's kind of hard to say, but like the formula that's in the paper that I actually should have right here, I don't know why I don't, is the accepted way of doing this. And so, yeah, it's just one of those kind of weird things that you just kind of, when you're using these things, you just sort of like say, it works for everybody else, so I'll just do it too. Yeah, question?
So are the positional encodings like constant from when you initialize the model?
Mm-hmm.
And are they kind of random?
No, they're not random. Like there's, I wish I had the formula, because maybe what I'll do at the end of this is just go look it up and I'll project it up here. But they're determined by the length that you allow in your encoder, like the length of the sequence, and then just your position, both your position in that sequence, and then the size of your like the dimension of your embedding. So once you have those 3 things worked out, these vectors are fixed.
So like if you made another instance of the model, given the same stuff, they would be the same?
Yeah. Yep, given those same parameters, they would be the same. Yep, that's exactly right. So I don't know. I don't have a better explanation of that. It works. So with 1 minute left, we spent all this time talking about what happens in the self-attention layer. Then we do a layer NOR. Then we do this feed forward, which actually expands the size of this, and then we contract it again, so that we can then add the input back in. We normally add the input back in, and that is that's the output. The authors of this have written on this part right here and have said they were really disappointed that they had to do this, because it's very weird to like. Typically, when you're encoding, you're always reducing the dimension. You're contracting the size of the dimension. You're not typically expanding, but somehow this expansion allowed for just these things to learn. And you can do your own kind of ablation study where you pull those out and see for yourself that the ability to project into a much larger space is really important for this for these encoder layers. So they're there as well, and you spit these out, and that's like your whole encoder module. Let's see, I can't remember. 1 second. Oh, yeah, okay, so I have a couple more slides. Let's go through these really fast because we've already talked a bunch about these. When we are decoding, the keys and values that we use in this attention, the attention heads here, come from the tokens of the encoder. So, and then the queries come from the tokens of the decoder. So this is how you get the dependence of the decoder on the encoder. Let's see. I'm trying to think what I was trying to show right here. I mean, I'm just showing, yeah, it's just showing the same thing, that we're bringing over the keys and the values. I think that's all of this. I just words I said here. The keys and the values that we use in that part of the decoder are from the encoder tokens. And it's the queries. If you think again about this, like what query key and value means, we want the keys and values to come from the encoder, but when we query, we're just going to we're going to be using the decoder information and then sort of like translate that into the like semantic information of the encoders, and that's really it. So, and this last part is just to say what I said a couple different times, is that we want, when we're decoding, we have this masking, and what that means is that like in sentences, those attention coefficients, we can compute all those, but if it's for a token that has come after the token we're trying to decode, then we set that attention coefficient to 0 so that it doesn't contribute to creating the values for that token while we're decoding. And I think that's the end of it. Yeah, I'm just reiterating the results that we saw before. Some additional results here. So next time what we'll do is we'll spend a little more time about like some of the nuances of this architecture, and we will and we'll talk about how these are trained. The training of these is really pretty cool. It's another example of self-supervision, but there's beyond just like predicting the next word. There have been proposed some really interesting ideas on how to train these things that make these even more powerful. And we'll see how using those turns these into like very general purpose like models, and like for language, for doing all kinds of language tasks. But we'll talk about that next time. These are ideas that come under the name of BERT and like related Sesame Street character names. So, yeah, that's it. Happy to. I'm sticking around now for the next hour. If you have homework questions or questions about the project or